So good evening, everyone. So today in this session, we'll be discussing the previous year questions of dual nature and radiation, right? So we'll be discussing the questions of de Broglie hypothesis as well as the photoelectric effect, right? So let's begin with the question number one, right? So these are all the PYQs we'll be discussing in this session. So starting with the question number one. The question number one says that the de Broglie wavelength associated with an electron accelerated by a potential difference of 81 volt is given by, right? So let's see how we can actually find the de Broglie wavelength when of an electron or of any object when it's accelerated by a potential difference of v volts, right? So we know that de Broglie wavelength is nothing, right? Lambda, that's equal to h upon p, right? Here p is the momentum, right? H upon p. H is the Planck's constant, right? And p is the momentum of the particle. So this is how we can calculate the de Broglie wavelength of any object, right? Now we know that the relation between the kinetic energy and the momentum of the particle is that p square over 2m is nothing. That's equal to the kinetic energy of the kinetic energy of the particle, right? That's the kinetic energy of the particle, right? So we can replace the momentum as that will be under root of 2m times the kinetic energy, right? And we can replace the momentum here in this equation with this, that's 2mk. So h upon under root of 2mke will give us the de Broglie wavelength when the kinetic energy of the moving particle is given, right? So this will be the associated de Broglie wavelength, right, for an object. Now it's given in this question that when an electron is accelerated, let's suppose when an electron is accelerated against the, or we can say through a potential difference, by a potential difference of 3 volts, right? Then the kinetic energy attained by the electron will be nothing. It will be the charge of electron multiplied by the potential difference. So this will be the kinetic energy gained by the electron, right? So in that case, we can replace this kinetic energy here in this equation with, that will be h upon 2me v, right? We have replaced the kinetic energy term with electron multiplied charge of electron multiplied by the potential difference, right? So from here you can say here that de Broglie wavelength for an electron is actually inversely proportional to the root of V, right? It's actually inversely proportional to the root of V, where V is nothing, it's the potential difference, right? It's nothing, it's the potential difference. Now we know that H is a constant here, M is the mass of electron, E is the charge of electron. All the three quantities are the constants here, right? For the electron, right? So if we calculate the values of all these constants here, we can write the de Broglie wavelength as 12.27 upon root of 3 in the units of angstroms, right? It's a very important relation to calculate the de Broglie wavelength of an electron, right? When an electron is accelerated through a potential difference of V volt, right? When an electron is accelerated through a potential difference of V volt, so we can use this equation to calculate the de Broglie wavelength associated with the electron, right? So in that case, in this question, that is 12.27, right, upon root of 81, because it's accelerated through a potential difference of 81 volt, it will be root of 81, or we can write it as 12.27 over 9, right? So it will be approximated to 1.36 angstroms, right? So this will be the de Broglie wavelength associated with an electron, which is actually moved by a potential difference of 81 volts, right? So these are some of the important equations through which, with the help of which, you can actually calculate the de Broglie wavelength of any object, right? And this is nothing. This is the de Broglie wavelength of electron, right? And let's move on to the another question. The question number 2 says that the maximum kinetic energy of the emitted photoelectrons in photoelectric effect is independent of, right? So we have to find the maximum kinetic energy, right? We know that whenever, let's suppose this is the metal surface, right? And we are incidentting photons or light energy, electromagnetic waves on this metallic surface, photosensitive surface, right? So if sufficient energy is supplied to the electrons present on the metal surface, then the photoelectric effect will take place, right? And let's suppose E is the energy supplied, E is the energy of the photon, right? E is the energy of the light supplied. Then some part of this energy will go to the work function of this electron, right? We need to unbound this electron from the surface of this metal, right? And that's what we call as the work function. And rest part of the energy of this photon will be present as kinetic energy of this electron, right? We can say that the total energy E will be nothing. It will be phi naught plus kinetic energy, right? Or the kinetic energy will be the maximum kinetic energy that the particle can have, that the electron can have. That will be E minus phi naught, right? And E is nothing. It's the equal to h nu, where nu is the frequency of the incident ray of light, and h nu naught is nothing. It's actually the uh, what we call as threshold frequency, right? U naught is nothing. It's the threshold frequency. It's the minimum frequency required to have a photoelectric effect, right? So this is nothing. This is what we call as threshold frequency, right? So to have a photoelectric effect, the light must have at least frequency equal to threshold frequency, so that photoelectric effect can be actually visualized, right? Or we can say the photoelectric effect can take place, right? So threshold frequency and so, the wavelength associated with that photon having the threshold frequency, we call that wavelength as threshold wavelength, right? Or we can write this kinetic energy hc upon lambda, where lambda is the wavelength of the incident photon. It will be equal to hc upon lambda naught, right? Where lambda naught is nothing. This is what we call as threshold wavelength, right? Threshold wavelength, right? This is the threshold wavelength, right? So the minimum energy of photon required to have the photoelectric effect, that energy we call as threshold energy, and the wavelength of that photon will be the threshold wavelength, and frequency of that photon will be threshold frequency, right? Now let's see. And I can see here, this is the work function, right? Phi naught, this is the work function here. It means that the kinetic energy greater the work function, lesser will be the kinetic energy. It means that it will depend upon the work function, right? So it depends upon the frequency as well. You can see the frequency term here, and it depends upon the wavelength as well. You can see the wavelength term here, right? Now, the only thing that it does not depend is the intensity. We know that for the photoelectric effect to take place, it will only depend upon the frequency of the incident ray of light, right? For the amount of, or we can say the number of photoelectrons emitted, it will depend upon the intensity, right? The number of photoelectrons emitted will depend upon the intensity. But for the photoelectric effect to take place, or we can say the maximum kinetic energy of the photoelectron, it will only depend upon the incident energy, because the source of the energy for this electron is nothing. It's the incident energy, and this energy only depends upon the frequency, or we can say it only depends upon the wavelength. The maximum kinetic energy cannot depend upon the intensity. It will only depend upon the wavelength of the incident photon. It will depend upon the frequency of the incident photon, or we can say it will depend upon the work function, right? So you can see here it will depend upon the work function. So maximum kinetic energy will be actually independent of intensity, right? It will not depend upon the intensity, right? Let's move on to the question number 3. The question number 3 says that the work functions of cesium, potassium, and sodium are given as, right? So work functions of cesium, potassium, and sodium are given as 2.14 electron volt, 2.30 electron volt, 2.75 electron volt, right? Respectively, right? If incident electromagnetic radiation has an incident energy of 2.20 electron volt, which of these photosensitive surfaces may emit photoelectron, right? So the question is that this is the photosensitive surface, and we know that the minimum energy required to have the photoelectric effect, right, should be actually at least equal to the work function of this metal surface, right? It should be at least equal to the work function of this metal surface, right? So this much of minimum energy must be incidented on the surface of this photosensitive device, right, or photosensitive material, so that the photoelectric effect will take place, right? That's what we call as the work function, right? So it means that the photoelectric effect will only take place if the energy incident is either equal or greater to the work function, right? The energy incident on the metal surface should be at least equal to the work function or greater than work function, right? Now you can see here the energy supplied is given as that's 2.20 electron volts, right? 2.20 electron volt. For cesium, you can see the work function is 2.14 electron volt and the supplied energy 2.20 electron volt. It means that the cesium will show the photoelectric effect. But for potassium and sodium, you can see the work function is actually greater than the incident energy. It means that the potassium and sodium will not show any photoelectric effect, right? So the only metal which will show the photoelectric effect here will be the cesium, right? Or we can say the only cesium will show the photoelectric effect, right? So C only cesium will be the correct answer for this question. Let's move on to the question number 4. The question number 4 says that the minimum wavelength of X-rays produced by an electron accelerated through a potential difference of 3 volts is proportional to. Right. Now let's see how actually the X-rays are produced. Right. Now this is the fast-moving electron. Let's suppose we are accelerating this electron against the potential through a potential difference of 3 volts. Right. Then the kinetic energy of this electron will be nothing. It will be the charge of electron multiplied by the potential difference, right? Once this electron moves in the forward direction, and this is the target, right? This is the target material, right? This is nothing, this is the target. So once this electron strikes this target, right? Strikes this target, then the electron actually lose its energy, right? The electron loses its energy, and that energy is actually appears in the form of the radiation, right? That energy appears in the form of radiation, right? So that energy is emitted in the form of radiation, and the frequency of that radiation is in the range of the frequency of X-rays, right? In the electromagnetic spectrum, right? Or we can say that for these fast-moving electrons actually, upon striking the target, produces the X-rays, right? They produce the X-rays. Now, the minimum wavelength, or we can say the maximum energy of the X-rays is possible only when whole of the kinetic energy of the electron actually gets converted into the uh, radiation, right? If whole of this energy gets converted into the radiation, or we can say the kinetic energy of the electron gets converted into the radiation, and the energy of this radiation will be nothing. It will be hc upon lambda, right? Let's suppose lambda naught is the wavelength of the X-ray radiation, right? So the maximum wavelength or minimum wavelength that can be there, it's hc upon E times V, right? Hc upon E times V. Now you can see from here, the wavelength of the X-ray is actually inversely proportional to the accelerated potential difference, right? It's inversely proportional to the potential difference, right? So this is the wavelength of the photon, right? Wavelength of X-ray. So don't get confused this wavelength. Don't confuse this wavelength with the de Broglie wavelength, right? We know that in case of de Broglie wavelength, the wavelength is directly proportional to 1 upon root V, or inversely proportional to root of V, right? But that's the concept of the de Broglie wavelengths. We are here talking about the X-ray productions, right? So here, this wavelength is the wavelength of the photon. It's not the de Broglie wavelength, right? And when we talk about the de Broglie wavelength of the photons, right? Remember one important point: the de Broglie wavelength of the photon is equal to the wavelength of that photon, right? So there is no difference between the de Broglie wavelength of the photon and the actual wavelength of the photon, right? It's the same, right? But in case of different materials, right? In case of uh, different classical objects, right? The de Broglie wavelength is different than that of the this wavelength of the radiation, right? So here we are talking about the wavelength of the X-ray radiation, right? Here in this case, the wavelength of this X-ray radiation is inversely proportional to the potential difference through which the electron is actually accelerated, right? We need to remember this equation, right? It's a very important point here. It was this was also asked last year in your NEET exam or JEE exam somewhere, right? So lambda is inversely proportional to the voltage or potential difference for the X-rays, right? So let's move on to the next question, right? Uh, so question number 5 is that the light ray is having photons of energy 4.2 electron volt, right? So light rays are having the energy of 4.2 electron volt, right? They are falling on the metal surface having work function, right? Let's suppose this is the metal surface, and this metal surface is having the work function of 2.2 electron volts, right? 2.2 electron volt. It means that the minimum energy required to have this photoelectric effect, right, is that should be equal to 2.2 electron volt. But the energy supplied on this metal surface is greater than that. So we can say that the stopping, we have to calculate the stopping potential, right? Stopping potential is actually the potential required, right? Reverse potential required so that the electron of maximum kinetic energy stops, right? Electron of maximum kinetic energy stops, right? That's what we call as the stopping potential, right? Now we know that the maximum kinetic energy the electron can have, that will be nothing. It will be the incident energy minus the work function, right? Now incident energy here is 4.2 electron volts minus the work function, that's 2.2 electron volt. So the maximum kinetic energy electron can have, that's 2 electron volts, right? So this is the maximum kinetic energy of the electron, right? Now we know that the kinetic energy, whenever an electron is actually moved in a potential, it's moved in a what we call as across or through a potential difference of V volts. We know the kinetic energy comes out to be equal to a charge multiplied by the potential difference, right? So once if 2 electron volt is the kinetic energy, 2 electron volt is the kinetic energy of this electron, right? It means that we need to apply the potential difference of at least 2 volts, right? 2 volts, so as to stop this electron, right? We need to apply the potential difference in the reverse direction of magnitude 2 volts, so that this electron of maximum kinetic energy will stop, right? So the stopping potential here will be nothing, it will be equal to 2 volts, right? So the stopping potential here will be nothing, it will be equal to 2 volts, right? Now, let's move on to the question number 6. The question number 6 says that the threshold frequency of a photoelectric metal is V naught. If light of frequency 4 V naught is incident on this metal, then the maximum kinetic energy of emitted electron will be. So the maximum kinetic energy of emitted electron is nothing. It's the incident energy, right? That's 4 times h nu naught, right? Minus the work function, that will be h nu naught. So that will be equal to 3 times h nu naught. So this is the maximum kinetic energy of the emitted photoelectron, right? Moving on to the question number 7, right? The question number 7 says that the number of photons per second on an average measured by the source of monochromatic light of wavelength 600 nanometer when it delivers the power of 3.3 into 10 to the power minus 3 watts, right? Where to find the number of photons emitted per second, right? Now the energy delivered per second, that's what we call as the power, right? So 3.3 into 10 to the power minus 3 joules of energy is delivered, that we will call this as power, right? So this is the power, right? So we can say in 1 second this much of much of energy is actually delivered, that's 3.3 into 10 to the power minus 3 joules. This much of energy will be delivered. Let's suppose n number of photons will be having this much of energy, right? This much of energy, that will be equal to h upon lambda, right? We have to calculate the value of this n. The value of h is given as 6.6 into 10 to the power minus 34, and c is the speed of light, that's 3 into 10 to the power 8, and divided by lambda. Lambda here is 600 nanometer, so it will be 600 multiplied by 10 to the power minus 9, right? So we'll just simplify it bit, right? So from here you can see it will be actually 6.6 into 3, right? Okay, 6.6 into 3, it will be 10 to the power minus 20, right? 10 to the power minus 26, not 28. 10 to the power minus 26. So divided by 6 into 10 to the power minus 7, right? Now from here, that's equal to actually 3.3 into 10 to the power minus 3, right? So it will be 1 and it will be 2 here, right? So this will be 3 and 2, and this and 2 and 2 will get cancelled once again, right? So we'll be having just 10 to the power minus 3 on a LHS 9 multiplied by. So it will be 10 to the power minus 19 here, right? So from here, the value of n will be nothing. It will be 10 to the power minus 3 into 10 to the power plus 19, right? So we can say the number of photoelectrons emitted per second will be nothing. It will be 10 to the power 16, right? So 10 to the power 16 will be the number of photons emitted per second, right? 10 to the power 16, right? So this much of photons, this much number of photons will be emitted per second, right? Moving on to the question number 8, right? An electromagnetic wave of wavelength lambda is incident on a photosensitive surface of negligible work. Actually, m mass is of photoelectron emitted from the surface has diploid wavelength of lambda t. Then relation between the two is, right. So the question is that there is a metal surface, right, and we are incidentting some light energy on this metal surface, and because of that, photoelectric emission takes place, right? Photoelectric emission takes place, right? And now it's given that the work function of this metal surface is negligible, or we can approximate it equal to 0. If m is the mass of electron, right, m is the mass of photoelectron, right. Now if work function of this metal surface is 0, it means all of the incident energy, that will be hc upon lambda, will be actually present as the kinetic energy of this electron, right. It will be present as the kinetic energy of the electron, because work function of this metal surface is equal to 0, right. Now talking about the de Broglie wavelength of this electron, we know de Broglie wavelength, that will be lambda t, that's nothing, that's equal to h upon under root of 2m times kinetic energy, right? I will calculate the kinetic energy from here. If we square it on both sides, it will be lambda t square, that will be equal to h square upon 2m ke, right? Or from here we can get the value of kinetic energy as h square upon 2m lambda d square. So this is the value of the kinetic energy, right? And this is also the value of the kinetic energy. It means both the kinetic energy will be equal to each other, right? Or we can say that hc upon lambda will be equal to h square upon 2sm lambda d square, right? Lambda d square. So from here h and h will get cancelled, right? So value of lambda will be nothing. It will be 2mc lambda d square, right, upon h. So this is the relation between the wavelength of the incident photon and de Broglie wavelength of the photoelectron, right? So this is the relation between the wavelength of the incident photon and de Broglie wavelength of the photoelectron, right? Now let's move on to the question number 9. The question number 9 says that light of frequency 1.4 times the threshold frequency, right? There is let's suppose this is the metal surface here, right? And we are incidenting some light of frequency 1.5 times threshold frequency. It means the energy of this incident photon will be 1.5 h nu naught, where nu naught is the threshold frequency, right? This is a photosensitive material. What will be the photoelectric current if the frequency is half, right? And now frequency is nothing, it's 1.5 times nu naught. Now if we do half of this frequency, it will be nothing, it will be 0.75 of nu naught, right? So this is the new frequency, right? It means that nu naught is the threshold frequency, the minimum frequency required to have this for the photoelectric effect to take place on this metal surface. That's the threshold frequency nu naught, right? Now the incident light energy is half of the threshold frequency, right? It's actually 0.75 times the threshold frequency, 0.75 times, right? So it means that the minimum energy is required is nu naught, right? But the energy we have, but the frequency we have, it's 0.75 nu naught, right? It means that this light will not be able to produce any photoelectron, or we can say no photo current will be there, right? No photo current will be there, right? No photo current will be there, right? So actually no photoelectron will be produced here, right? No photoelectric current. So let's move on to the question number 10. An electron is accelerated from rest through a potential difference of V volt if the de Broglie wavelength of the electron is 1.227 into 10 to the power minus 2 nanometer, right? So this is the de Broglie wavelength of the electron, right? So if lambda d is given as, that's 1.227 into 10 to the power minus 2 nanometer, that's 10 to the power minus 9, right? Or we can write it as 1.227 into 10 to the power minus 1 angstrom, right? This we can write here, right? So this much angstrom is the wavelength, right? We know the de Broglie wavelength of this electron is nothing, it's 12.27 upon under root of V, right? In the units of angstroms, right? We have to find this potential difference, right? You can just substitute the value wavelength here, right? From here you can easily calculate the value of this V, right? So the only variable here is the potential difference. You can easily calculate the value of V here, right? Now let's move on to the question number. This is one of the important questions, right? It was asked in your one of the exams, right? An electron of mass m with an initial velocity vector v is equal to v naught I cap, right? Initially, the electron was moving. The electron was moving along some, let's suppose along this direction with the velocity of v naught I cap, right? Enters a electric field. The direction of this electric field is given as it's minus e naught I cap, right? This is the direction of the electric field, right? If lambda naught is its de Broglie wavelength initially, right? Initially, its de Broglie wavelength is given as lambda naught, and that lambda naught will be nothing. It will be h upon mv naught, right? So this is the de Broglie wavelength of this electron, right? we have to calculate then its de Broglie wavelength at later time t is, right? Now, once this electric field is set, there will be electrostatic force on this electron, and the electron will be accelerated, or we can say the velocity or speed of this electron will change, right? If the direction of this electric field is along this direction, then the force on this electron will be equal to E times E naught along this direction, right? Along forward direction, or we can say that the external force actually favors the velocity of this electron, right? Or we can say speed of this electron is going to increase, right? It will be moving with a constant acceleration of E naught upon m, right? So we can see the speed of this electron after some later time t. It will be v naught plus at. A is given as E naught upon m multiplied by t, right? Now the wavelength at some later time t will be nothing. It will be h times mv, where v is v naught plus E naught upon m multiplied by t, right? So from here it will be h upon mv naught plus E into E naught t, right? So this will be the wavelength of at some later time t, right? We can replace this h mv naught. We can replace this h value of h here with uh, lambda naught mv naught, right? It will be lambda naught mv naught, right? Divided by mv naught plus E naught t, right? Or it will be equal to lambda naught upon 1 plus E naught t upon mv naught, right? So this will be the wavelength, or we can say this will be the de Broglie wavelength at some later time t, right? This will be the de Broglie wavelength at some later time t, right? So this is how we can calculate the de Broglie wavelength when an electron or any particle is accelerated through some acceleration because of the external force, right? Let's discuss this question number 12. When the light of frequency 2 mu naught, where mu naught is threshold frequency, is incident on a metal plate, the maximum velocity of electrons emitted is v1. Okay, when the frequency of the incident radiation is increased to 5 v naught, the maximum and velocity of electrons emitted from the same plate is v2. The ratio v1 to v2 is, right? So maximum kinetic energy will be nothing. It will be half m v1 square, right? That will be equal to when the light of frequency 2 nu naught, right? Okay, so it will be 2h nu naught minus h nu naught, right? And for the second case, the second kinetic energy will be half mv2 square. It will be, since the frequency of the radiation has been increased to 5 nu naught, it will be 5h nu naught minus h nu naught, right? So it will be actually equal to 4 times h nu naught, right? Now we can just divide these two equations. It will be v1 by v2 whole square, right? That will be nothing. It will be equal to 1 upon 4. Or from here, v1 over v2 will be nothing. It will be 1 ratio 2, right? 1 ratio 2. So this will be the answer, right? 1 ratio 2 will be the v1 ratio v2, right? Moving on to the question number 30, right? The de Broglie wavelength of a neutron in thermal equilibrium with heavy water at a temperature T, Kelvin, and mass m, right? So we have to find the de Broglie wavelength for this neutron, right? The Broglie wavelength of a neutron, right? So it's in thermal equilibrium with some heavy water, right, at some temperature T. So the thermal kinetic energy of this particle or this neutron will be nothing. In 3 degrees of freedom, it will be 3 by 2 kT, right? For each degree, it will be half kT. For 3 degrees of freedom, it will be 3 by 2 kT. So this will be the thermal kinetic energy of this neutron, right? So the de Broglie wavelength associated with neutron will be h upon under root of 2m times kinetic energy of the particle, right? So it will be h upon under root of 2m. Kinetic energy of this particle is 3 by 2 kT, right? So 2 and 2 will get cancelled. It will be nothing, h upon under root of 3m kT. So this is the de Broglie wavelength. This is the de Broglie wavelength present or associated with this neutron, right? So let's move on to the question number 14. Electrons of mass m with de Broglie wavelength lambda follow the target in an X-ray tube. The cutoff wavelength lambda not of the emitted X-ray is, right? So we have to find the cutoff wavelength, right? We know that whenever suppose electron is accelerated with some against the potential difference of V, the kinetic energy of this electron will be nothing. Charge of electron multiplied by the potential difference, right? So this is the target here, right? The electron will strike this target, right? What will happen? The electron will lose its energy and the energy will appear as the radiation, right? The energy will appear as the radiation, right? it will appear as electromagnetic radiation, and the energy of that radiation will fall in the X-ray region of the electromagnetic spectrum, right? It will fall in the X-ray region of the electromagnetic spectrum. So these are the X-rays produced, right? These are the X-rays produced. So the maximum kinetic energy can be converted, if the maximum kinetic energy get converted into the production of these X-rays, right? So EV will be nothing, it will be equal to Hc upon lambda, right? So lambda naught will be nothing, it will be Hc upon EV. So this is the minimum wavelength that we can have, a minimum wavelength that we can have, so that the X-rays are produced, right? Uh, so this is how actually the X-ray production takes place, and this is how we can calculate the minimum wavelength for the X-ray production, right? So let's move on to the question number 15. The question number 15 is about the conductivity of a photodiode, right? And photodiode, we know it's a semiconductor device, right? It's a semiconductor diode, right? And we know that in case of semiconductors, what happens is that conduction takes place in the conduction band, right? And there is no conduction in the valence band, right? So in order, when there is no electrons present in the conduction band, then the conductivity is zero. So in order to have the conductivity or have some conductivity, what we do is that the electron must jump from the valence band to the conduction band, so that the conductivity takes place, and the energy gap between the two bands, that's the valence band and the conduction band, that's what we call as the band gap, right? That's what we call as the band gap. So the question is that the conductivity of photodiode starts changing only if the wavelength of incident light is less than 660 nanometer. The band gap of photodiode is found to be it's x upon 8, right? It's here x upon 8, right? The value of x is, right? So the x upon 8 is the band gap. We have to find the value of x, right? And we know that the question says that the minimum wavelength we need is 60 nanometer or less than that, right? It means that we can just take this as the minimum wavelength required to have the electron in the conduction band, or we can say so that the electron will jump from the valence band to the conduction band, right? So 660 nanometers, right? So energy equal to the 660 nanometers of this photon will be actually the band gap of this valence band and the conduction band as well, right? That's actually given as x upon 8. So x upon 8 will be nothing, it will be equal to uh, energy gap here, right? We can write it as hc by lambda here, right? Or there's a very important shortcut also, right? That's we can write it as hc, value of hc is 1240, right? 1240 upon lambda, right? But it will be here in the 1240, it will be nanometers, electron volt, right? Nanometers electron volt. So if lambda is in nanometer, the nanometer and nanometer will get cancelled, we'll get the energy in the form of electron volts. So we can write it as 1240 upon 660, right? So from here, this and this will get cancelled, it will be 11, right? So it will be 124 upon 66, right? So it will be actually, so 124 upon 66, it will be 62 upon 33, right? And therefore the value of x will be nothing, 62 upon 33 multiplied by 8, or we can approximate it to be equal to 32, it will be 8, 4, 32, right? So it will be 62 upon 4, right? 62 upon 4, that will be actually equal to 31 upon 2, or we can say approximated to equal to 15.5, right? 15.5, right? So 15.5 or 15 will be the value of x, right? 15 can be the value of this x, right? So this is how we can actually, or if you want to calculate the exact value of x, then what we have to do is that you have to just use all these given values here, right, to calculate the exact value of the x, right? Take the value of h equal to 6.6, right, and the charge of electron as 1.6, right? Now let's move on to the question number 16. The question number 16 is that when a metal surface illuminated by a light of wavelength lambda, the stopping potential is 8 volts, right? We know that the stopping potential is nothing when the potential required to actually stop the electron of maximum kinetic energy, right? So it will be h nu minus h nu naught, right? Now it's given that the stopping potential is 8 volts. It means that the maximum kinetic energy of that electron would have been 8 electron volts, right? When the same surface is illuminated by a light of wavelength 3 lambda, right? If a light of wavelength 3 times lambda is actually incidented, right? Stopping potential is 2 volts. It means definitely the kinetic energy of the electron will actually decrease, right? Or we can say here in this case it will be hc upon lambda, right? Minus hc upon lambda naught, right? That will be equal to kinetic energy of the maximum kinetic energy of the photoelectron. That's given as 8 volts, right? It will be 8 electron volts, right? 8 electron volts. And similarly, when the surface is illuminated by a light of wavelength light of wavelength 3 times lambda. So it will be hc upon 3 times lambda, right? And we know that the threshold wavelength will not change. It has to be a constant, right? It has to be a constant. The stopping potential is 2 volts, or we can say the kinetic energy will be 2 electron volts, right? 2 electron volts. What we have to do here is that we have to find the threshold wavelength for this surface, right? We have to find the threshold wavelength for this surface, right? So what we'll do here is that if we divide here by 3 on both sides, right? Or what we can do is that this is the equation. If we divide or if we multiply here this equation with the 3 on both sides, multiplying this equation with 3, so we'll be having hc upon lambda here, right? Minus 3 hc upon lambda naught here, right? That will be equal to 6, right? 6 electron volts, right? 6 electron volts. So let's take this equation 1 and take this equation second, right? Now what we do here is that we'll just subtract first from second, right? We can subtract first from second or second from first, right? Let's subtract second from first, right? So it will be hc upon lambda minus hc upon lambda naught, right? So it will be minus hc upon lambda. It will be plus 3 hc upon lambda naught, right? That will be actually equal to 8 minus 2, that will be 6. So from here, this and this will get cancelled, right? So 3 hc upon lambda naught minus hc upon lambda naught, it will be 2 hc upon, right? That will be equal to 6, right? So this and this will get cancelled, it will be 3, right? Now, in order to calculate the wavelength of this electron, wavelength of the threshold wavelength of this metal surface in terms of angstroms, right? Then we have to take the value of this Hc as 12400, right? 12400. So if we take it as 12400 divided by 3, that will be equal to lambda naught. It will be in the units of angstroms, right? It will be in the units of angstroms, right? So this will be 3, 4, right? 3, 4, and it will be 1, right? So it will be approximately 4100, right? It will be 4100. We can say 4100 will be the angstroms. 4100 angstroms will be the threshold wavelength, right? 4100 angstroms will be the threshold wavelength for this metal surface, right? So this is how we can calculate the threshold wavelength for the given situation, right? Now let's move on to the next question, the question number 17. For the photoelectric effect, the maximum kinetic energy of the photoelectrons is plotted against the frequency of the incident photons as shown, right? So kinetic energy as a function of the frequency. So kinetic energy is nothing, it's h nu minus h nu, right? And you can see here h is a constant, mu naught is a constant. So if we plot the kinetic energy as a function of frequency, right? As a function of frequency, you can see here that minimum at least we need the frequency equal to the threshold frequency so that the photoelectric effect takes place, right? Photoelectric effect takes place, right? Now plotting this graph between kinetic energy, right, versus the frequency, right? Now you can see here it's a positive slope but with a negative intercept, right? It means the graph should be like this, right? Graph should be like this. So this should be the graph between the kinetic energy and the frequency, right? We're talking about this theta here slope. This will be nothing. It's the slope, right? Tan of theta. So from here you can see the tan of theta is nothing. Tan of theta, it will be actually. So h nu naught will be the intercept here, right? it will be intercept, and h is the slope, right? It will actually give the Planck's constant, right? We can calculate the Planck's constant, right? The slope will here give us the Planck's constant. So it's a very important question, right? We can calculate the value of the Planck's constant using this Einstein's photoelectric effect equation, right? Einstein's equation of photoelectric effect to calculate the Planck's constant, right? The slope will give us the Planck's constant, right? So question number 18, right? The question number 18 says that the work function of a substance is 3 electron volt, the longest wavelength of light that can be that can cause the emission of photoelectrons from this substance is approximately the longest wavelength of the light, right? It means the minimum energy, right? If the wavelength is longest, it means the energy has to be minimum, right? So it means that the minimum energy, and we know for a minimum energy required for a substance for the photoelectric effect to take place is the work function, right? It means that the longest wavelength of the photoelectron that can be there will have energy actually equal to 3 electron volts, right? Equal to the work function, right? So we have to calculate this longest wavelength, right? So 3 electron volt, that will be the energy of this photoelectron, that will be h upon lambda. So in terms of V12400, right? Upon lambda, we get the value of lambda 12400 upon 3 in the units of angstrom, right? So this will be the longest wavelength, right? So this will be the longest wavelength. So if we further increase the wavelength greater than this, right? If let's suppose this is lambda naught, if we have a wavelength greater than lambda naught, then it's for sure the photoelectric effect will not take place, right? There will be no photoelectric effect if the lambda is greater than the lambda naught calculated here. The longest possible wavelength for the photoelectric effect to take place here will be 12400 upon 3, right? This much angstroms will be actually the possible longest wavelength, right? For the photoelectric effect to take place, right? Moving to the question number 19, the two sources of light emit with a power of 200 watt, the ratio of number of photons of visible light emitted by each source having wavelengths 300 nanometer and 500 nanometer respectively is. It's given that two sources of light emit with a power of 200 watt, right? Each of these sources are having 200 watts, right? Okay, so we have to find the number of photons emitted by each source per second, right? So it means that 200 joules of energy will be actually emitted per second, right? For each of them, right? It will be N1, right? Hc upon lambda 1, right? And for second, it will be 5, once again, 200 joules of energy emitted per second, right? Let's suppose N2 electrons are N2 photons are emitted per second, right? It will be Hc upon lambda 2, right? Now from here you can see that so N1 Hc upon lambda 1, right? That will be equal to N2 Hc upon lambda 2, right? So Hc and Hc will get cancelled. So N1 upon N2 will be nothing. It will be actually lambda 1 upon lambda 2, right? Lambda 1 upon lambda 2. The value of lambda 1 is 300 and value of lambda 2 is 500. So ratio will be nothing. It will be 3 ratio 5, right? 3 ratio 5, right? 3 ratio 5 will be the ratio, right? So that's it for today, for this session. And in this session, we have almost covered each and every topic and concept of photoelectric effect and dual nature, right? Each and everything has been covered, right, in this lecture, right? So what we'll be doing in the next lecture, we'll be starting with the atoms and nuclei on Monday, right? So we'll meet on Monday with atoms and nuclei. Till then, take care and goodbye.